Good morning, and we're going to talk about graphing exponential functions. And what we want to be able to do at the end of this lesson is we want to be able to identify exponential functions. We want to be able to determine the domain and range of exponential functions. And then we want to be able to graph these exponential functions. Let's see here. Some of the things that we're going to have to know. Exponential growth and decay. Now, before I go into this, I will say that these are some of you should have been exposed to this and learned this material in Algebra 1, and this is just an expansion of what we already know. Especially when we look at characteristics of domain and range. Those are referred to as my x and y values, right? My input domain, my x, my input is you have my range, my output, my y values. And then asymptote. Asymptote is, referring to that point that we're going to get really close to but never touch. Often, we speak about it sometimes in our in behavior of functions. And if I look real quickly at just a graph of an exponential equation, it may appear to be something like this. Whereas my x increases, my y increases, so that is my exponential growth. But right here, we are heading back as my x approaches negative infinity. My y is going to approach some value that, it just keeps getting closer and closer to, but never touches. So just simply drawn, it would seem that this function is approaching 0, right? Y is 0, but never crosses over that. And we'll talk more about it in the future, but again, it's because no matter what I put in for the variable, I'm never going to be able to equal 0. So let's see here. Looking at the domain and range, this function goes on forever in both directions because even as I have this drawn right here, it's going to go on forever to negative infinity on my x-axis, and then positive infinity, it's technically going to go on forever. It's just going upward faster than it is going outward. So my domain, the domain of my function is going to be all real numbers because it is all real numbers, all real values of x is going to be my domain because I can put any number, any value of x into my functions, and then the value of y will be determined by my transformations. So, and we'll talk more about this, but let's see. Going on to our next information here. Identifying exponential functions from a table. Now, you may recall again from algebra, as I look at my parent function here, y equals, or equation, function, however you want to look at it, y equals b raised to the x power, or f of x equals b raised to the x power. Some of the characteristics that you're going to see as my x value increases by 1, looking here, my x value increases by 1, my exponent is going to increase, thereby we're multiplying my base by a number. And that may seem a little bit ambiguous here, but looking at the characteristics here, if we look at this first table right here, my x values are increasing by 1, right? Plus 1. And then my y values are increasing by some factor. And let's see, as I go from here to here, we decreased by a quarter. As I went from here to here, looks like we multiplied by 1/2. When we went from here to here, we multiplied by 1/2. When we went to here, we multiplied by 1/2. So the rate of change here is 1/2. We are multiplying over and over again by 1/2 to get the next term. So that identifies my b value, right? The growth factor, or the growth decay, or of my function. So I have something along the lines of y equals 1/2 to the x power, because each time, let's see here, f of x, let's do that, equals 1/2 to the x power. And now if I were to, now I was able to create that, we might say, hey, well, I know more and I've been at greater experience with these, but let's just do some values here and see if this function is going to work. So as I went ahead and created a table real quick, and I plugged in values of x into my function or equation, and so I have 1/2 raised to the x power. Well, 1/2 to the first power is 1/2. 1/2 raised to the second power is going to be 1/4. 1/2 raised to the third power is 1/8, and 1/2 raised to the fourth power is going to be 1/16. And if you notice, right, that's what we have right here is my output. So this is an accurate exponential function. My ratio here that is changing is going to be my b value as long as I see this change of 1. And I have a constant ratio change. And if, say, you couldn't say, oh my gosh, what is going on here? I can't figure it out. Well, what you can do is take one number, take one of those numbers, 1/4, and then divide it by, I said 1/4 and wrote down 1/2. Take 1/4 and divide it by the previous number. Well, we would simplify that, and then that would become, looks like it would simplify to 1/2. So that's how we find that, is we take one term and divide it by the previous term. So let's see here. If we look at this next example, what is changing as we went from here to here? As we went from here to here? As we went from here to here? Well, 1/2 times 2 is going to be 1. 1 times 2 is going to be 2. 2 times 2 is going to be 4. So looking at that, it looks like the b value is equal to 2. So I have f of x is going to be equal to 2 to the x power. But wait a minute, did I check this? Yeah, sure enough. +1, +1, +1. So as my x value is changing by 1, my y value is changing by some ratio. And again, I did say that if you take one term and multiply it by the previous term, and we'll use, I just take 4 divided by the previous term is 2. So there you go. We're able to find that. So here is my exponential function. And doing the same thing here with this next I have my x value is increasing by 1, right? And then my y value is increasing by, well, if I take 9 and divide it by the previous term, that is 3. Okay, that seems to be times 3. If I take 3 and divide it by the previous term, that's 3. So sure enough, it's changing by a factor of 3. So then b is going to be 3. So I have f of x is equal to 3 to the x power. So you can, by the characteristics of the table, figure out what is going on with, is that an exponential function or not? So let's see here. Moving forward, exponential growth, graphing. Everybody loves to graph. So as I look at this, I'm going to go ahead, and the best thing for us to do is to create a table, plug some values in, and get some values out. So I have x, y, I have 6 to the x power, and I'm going to start with, let's go with -1. 0, 1, 2, 3, 4 maybe. So that is going to be, all right, so if I plug in some values to where I can graph, and I'm going to go ahead and plug in -1, 0, 1, 2, 3, 4, and that would be 6 raised to the -1 power, which is 1/6. 6 raised to the 0 power is going to be 1. 6 raised to the first power is going to be 6. 6 raised to the second power is going to be 36. And I went ahead and stopped right here. Looking at my graph, if I try to graph something raised, we're talking 218, I'm not going to create a graph that. I'm not even at this rate going to create a graph that goes up to 36, but I can see what's going on here. I can say when x is 0, when x is 0, right here, my y value is going to be 1. And if you look at my increments, you should be able to see that I'm going 2, 4, 6, 2, 4, negative 2, negative 4. And then let's see here, go ahead and graph the next point, which is going to be 1, 6, 1 and 6. Then we also have negative 1 and 1/6. So hard to see here, you know, just because the numbers, but we're doing this. We're doing that. That is my exponential growth function. And looking at the exponential growth, as we become positive on the x-axis, the y is also becoming positive. And let's see if we could possibly do another number here. But before that, if we think about the asymptote, the asymptote is that number that the horizontal asymptote is going to be the value that we approach but never touch. And what we find here is as we keep getting towards the negative infinity, I'm going to keep approaching 0, but I'm never going to cross over that. So in this case, my asymptote is y equals 0. Let's see here, and if I were to try and graph another equation that would be exponential growth, let's go for f of x equals, we'll go 3 to the x power. That's, you know, instead of 6 to the x power. So when we do that, so if we have, I've went ahead and gone ahead and plugged in negative 2, negative 1, 0, 1, and 2 for the x value. So when I plug that in, I end up getting my outputs of negative 1/9, 1/3, sorry, not negative 1/9, just 1/9, 1/3, 1, 3, and 9. So when I graph that, you'll notice that looks like my y-intercept is going to be the same. I'm going to have 1 is 3, 2 is going to be 9, and then I have the same asymptote of y equals 0. So that would be my function f of x equals 3 to the x power. Again, it's exponential growth. And then I will just add here that it says one of the rules is when b is greater than 1. Well, if I were to look at that and say, why do I have that rule? Well, if b is 1, right, y equals 1 to the x power. Well, that is going to be, no matter what I put in for x, the output is going to be 1. 1 raised to any power is just going to be 1. So if I were to graph, that would end up looking just like a straight line. Just like a straight line. So that's not exponential function, that's linear in that case when I graph it. So just keep that in mind that it's not growing. So here we talk about decay. Now decay, exponential decay is going to be when b, right, is going to be in between 1 and 0. So it's a portion of something. We're constantly taking away. So right here, each time my x increases, I'm going to be multiplying by 1/3. So I'm going to be decreasing by 1/3 each time. In this equation, if my b value is 1/5, every time x goes up 1, I multiply by 1/5. So it's going to be taking it away and making it smaller. And then in essence, this graph will look like this because it's going to be approaching, the larger my x value gets, the smaller my y value will be. So we'll do some tables here and then graph. Okay, so as I plugged in some values here, I just went from -2 to a +3, and of course I input the x value in for my variable and came out with some y value. So we can see that 45 is a pretty high value for y. Then we get down to 15, and then when x is 0, we're at 5. Then when x is 1, we're at 5/3, which is, what's that? 5/3 is almost 2. Then when x is 2, we're at 5/9, which is just a little bit more than a half. And then we keep approaching closer and closer. So something like this, obviously not perfect, but where I look at this equation, as x approaches a positive number, I'm decreasing, I'm decaying at a rate of 1/3. So this would be exponential decay. I used to be a very high value of y, and we are decreasing to a very low value of y, and it's approaching 0. So my asymptote is going to be y equals 0. And let's see here, looking at this next equation right here, x is -2, we're looking at 25. When x is -1, we have 5. So I can start graphing there. When x is -1, we have 5. When x is 0, we have 1, and then 1/5, and then 1/25. So looking here, it's decreasing exponentially again, and my y equals 0 is going to be my asymptote. So just looking at those characteristics of decay, and it's decaying at a rate of, this equation is decaying at a rate of 1/3. This is decaying at a rate of 1/5. So we're constantly taking 1/5 away and 1/5 away and 1/5 away. We're never going to get to a 0 value. It's just going to be a very small sliver of what was originally there. So that's why we approach 0 but never touch it. And going on here for translations and reflections. Okay, so the parent function that we're looking for here is this thing. It is y equals b raised to the x power minus h, and then plus k. Just like we've experienced in other transformations, the h is going to move the function left and right. The k is going to move it up and down. So I can do table values and come up with some table values here. I can come up with some table values here. I can come up with some table values here. But I guess maybe let me add one function in here of, we'll call it h of x just for the fun of it, for the heck of it, 4 to the x power. And then what we're doing here is we can see some transformations going on that way. If this is my starting function, here if I have 4 of x minus 5, that means here my k value is minus 5, so I'd move this function down 5. Looking at the 4 of x again, from here I'm going to move the function down 3 and right 2. Again, right here, I'm going to move the function right 5 and up 3. So we'll be able to see what's going on here with our functions. And then when I have a negative x value, all that's going to do is reflect my function over the axis, much the way a did when we were dealing with a quadratic or root function. So let's go ahead and I'm going to graph a couple of these. Okay, so what I've done is I've gone ahead and I've input this information into the calculator. I have put in an x value and received the output of a y value. And you can see them here as I have 4 to the x power, my inputs and then my outputs. When I have 4 to the x power minus 5, my inputs and outputs. And so as I graph these, as we graph a handful of these, so it looks like -2 and very close to 1/16, but very close to 0. -1 is going to be a little bit higher up, and 0 is going to be 1. 1 is going to be at 4. 2 is going to be at 16. So we have this exponential function doing this right here. That's what my exponential function is doing, and this is the f of x equals 4 to the x power. Now, when we go to graph f4 to the x power minus 5, what we are finding here is when x is 0, I'm going to be at negative 4. When x is 1, I'm going to be at negative 1. When x is 2, I'm going to be at 11. And then when x is 3, I'm going to be way up there somewhere. And then when x is negative 1, I'm going to be at almost negative 5. So here's the shape of that function. So it looks like the only thing that's happened is my function has just been moved down 5, which is what that is indicating. Let's see here as we go to this next function, as I plug the values in, negative 2 is going to be almost negative 3. Negative 2 is going to be almost negative 3. And then negative 1 is, again, going to be still very close to negative 3. And 0, looks like negative 2 is going to be negative 2. 3 is going to be 1. 4 is going to be 13. So this one does something like this. And what has happened is the function has been moved. It has been moved right 2, right? It's been moved right 2, and then it has been moved down 3. But otherwise, it's the same general shape, right? 4x. And then it's just how it has been moved around. And then we have, last but not least, the blue function here, which is 4 to the x minus 5 power plus 3. And notice, before we even graph it, as I'm really noticeable here in the decimals, that after I hit 4, I'm getting 4 1/4, 4 1/16, looks like 4 1/64. I'm getting three. I'm getting very close to 3, and my decimal keeps getting smaller, but I'm never going to get to 3. So 3 is actually going to be my asymptote. So that's how we can start seeing that, is it keeps getting closer and closer to 3, but never touching it. So when x is negative 2, be somewhere along that lines. When x is 0, it'll be somewhere along that line. When x is, let's just go to 5, right? When x is 5, it's going to be 4. And then when x is 6, it's going to be 7. So there we have this function taking shape right there. Same general shape, just has been shifted around, translated around the coordinate plane, okay? And then, of course, we have our, some examples here of reflection, right? So if I have y equals 3 to the x power, when I plug in some x and y's, and then I'm going to have y is equal to 3 to the negative x, and I'm going to plug in some x and y's, or x and get out the y's. Okay, so I've plugged in some values here, and as you can see, just by looking at the tables, well, it looks like my look at my y values. They seem to be a bit reversed here based on that negative. So when I go to graph it, graphing this function first, or this equation, when I have negative 2, right, I have almost 1, or almost 0, and I keep getting bigger until I hit that point right there, and then I'm going to have 1 and 3. I'm going to have 2 and 9. So this function looks like this. And then my orange function is going to, when I graph it, I'm going to have negative 2 and 9. I'm going to have negative 1 and 3. And it looks like that reflection, that negative, is going to cause it to reflect across the y-axis. So just seeing some of the characteristics that's going on here. And let's see here, stretching and compressing. Well, Let's see, I'm not going to graph these, I guess. Hold on one moment. All right, so as we look at our stretches and compressions, if we start off with just a function with y equals 2 to the x power, right? I have this thing right here. It's going to be my function. Now, if in essence my outputs, when I look at this next one, 2 times 2 to the x power, whatever my outputs are going to be multiplied by 2. So here, when I plug in x and y, right here, when x was 0, when x was 0, my function was 1. Here, when x is 0, y is going to be 2. So I'm going to start seeing multiples. Things are going to be multiplied by 2. When x was 1 in my first equation, sorry, I guess I should keep them color coordinated, that is going to be 2. Here, when x is equal to 1, that is going to be 4. So I'm going to start seeing my numbers being multiplied. So just, looking at these characteristics will help to identify, just the stretches, just knowing what's going on there. So we have 1 and 2, and then we have 2 and 4 right there. Then we have 1 and 4. And then we have green, we're doing this thing where we keep getting stretched, faster moving, stretching upwards. And then of course blue, we'd be multiplying everything by a half, right? When 2 would be 1, that would be a compression. So we're able to look at some of the characteristics based on, what are those factors being multiplied by the parent function or the base function to see how it's going to stretch or compress it, the function. All right, so as we're graphing these exponential functions, being able to identify what an exponential function looks like, determining the domain and range, remembering that the domain is going to be all real numbers. And then our exponential growth, we're looking at exponential growth is going to look like something like that. Exponential decay is going to look something like that. And then, it can be stretched and compressed or translated, reflected, those kind of things based on its characteristics. And it just takes a little bit of practice with the graphing, putting in an input, getting out an output to get those things on a graph and see what their characteristics are and how they've been moved around from the parent function.